Hi everyone, in this session we'll be looking at measurements and uncertainties and what they mean. We're going to start firstly with what systematic errors are and random errors in measurements mean. We're going to look at precision and accuracy, very important language in physics. Also we're going to analyze what we mean by absolute percentage uncertainties and how to deal with them when we add, subtract, multiply, divide, and raise to powers. And then we will leave the last one at the end, is the graphical treatment of errors and uncertainties. Okay, so the first thing we'll start with is with errors. Now, what an error is the difference between a computed value or a measured value and a true or theoretically correct one. So in other words, simple words, is an error that can occur that will cause your experimental value, for example, to vary from the actual accepted one. So let's say you've done an experiment and you found the gravitational field strength to be, for example, 9.17 meters per second squared. Obviously, it carries an error, so there was an error in acquiring this measurement when we know that naturally this value should be 9.81 meters per second squared. Obviously, this value varies in different regions around the Earth, but roughly it should be around that value. So there are two errors that you should know of, and then there's also categories that we name different errors through. One of them is the random errors and systematic errors. I'll talk about human error, zero error, and parallax error and what they usually are. So random errors are usually caused by unknown and unpredictable changes during experiments, meaning that, for example, it's something that you can't control and something that you can't really measure or see straight away. It's quite hard to pinpoint them and narrow them down what caused the errors in your experimental values. They usually occur due to changes in environmental conditions or due to problems with certain instruments. So for example, if you were doing an electrical experiment, so you had an electrical circuit, it could be that the temperature of the wire got higher at one point while you were taking measurements, and hence it affected your results, and so on. Now, usually when you see the results plotted and they have random errors, you'll notice that they're scattered randomly above or below the line of best fit. So for example, if this was my graph, then points around the line of best fit would look like that. So you have random points up and down. There is no particular pattern to them, but there is clearly that since these points don't fit straight directly onto the line, they have been caused by random errors. That's why what we usually do to avoid the effect of random errors, we will repeat 3 or 4 different measurements for the same measurement that we're making. So when we repeat and take an average, it kind of removes some of the effect of random errors. Now that's a very different error. Random errors are different from human errors, which is like usually a one-off mistake. It can be very easily spotted. So for example, if you were measuring the length of a spring and one of your measurements was 4.1 centimeters, another one was 4.2 centimeters, and another one was, for example, 10 centimeters. Obviously, you'll think, okay, wait a minute, why is my length changing so extremely? So that's just usually a simple one-off mistake. But like I said, this is not one of the main errors. What we are interested is the random errors, systematic errors, but you should also be able to pick out what we mean by human errors. Now, the second very important errors are systematic errors. These don't happen by chance, so it's not like the random errors where these unpredictable things that you can't change, you can actually change what affects systematic errors. It's usually due to an inaccuracy in the apparatus or by the way the person's conducting the experiment. And you'll see two effects below it here of what could cause that. So what that does, it basically shifts all the measurements in the same direction. For example, a zero error is a type of systematic error where an instrument is not properly calibrated, so it gives a non-zero value when the true value is supposed to be zero. That could be with a thermometer, for example. So if the thermometer there is not calibrated properly to show 0 degrees Celsius when it's 0 degrees Celsius and instead shows, for example, 0.2 degrees Celsius. It depends obviously on the increments that it increases by, but let's say it shows 0.2 degrees Celsius when it's supposed to show 0 degrees Celsius, then all of the values will be shifted by 0.2 degrees above of what the actual value is supposed to be. So that's a systematic error. It's an inaccuracy due to the apparatus, which shifts all the measurements by 0.2 degrees in this case. Another one could be that an analog ammeter. So analog ammeters are the ones with the needle. So you have numbers around, and then you have a needle that's supposed to point right at 0. And instead of pointing exactly at 0, it could point at, for example, 0.3 amps. So ammeter. Ammeter is what measures current, remember that? So that means that all of your measurements of current will be 0.3 above what they're supposed to be. That is a systematic error. Now, what we mean about a person causing causing systematic errors while they're conducting the experiment is usually through parallax error. So basically reading the scale at the wrong angle. This is something that we constantly mention, and you probably see mostly when you are measuring, using it to measure the volume in a measuring cylinder. So you have a measuring cylinder and you're trying to take a measurement, your eye should not be looking above it. Your eye should be right directly where the level of water is or whatever you're measuring, fluid, so that you can get the actual measurement. Parallax error is just caused by looking at it from the wrong scale. That can even happen with a ruler. If you're looking at the ruler from one side instead of looking at it directly at the top of your measurement that you want to make, you will get it a bit wrong because of the angle that you're looking at it through. We will see that mostly through experiments as well. You'll experience it through experiments. But just to summarize very quickly, random errors are quite unpredictable. We can't usually narrow down where it comes from, whereas with systematic errors, we can narrow it down, and it will also appear in your results in a graphical experiment. So for example, if the line is supposed to go through the origin, instead, if you have all your results plotted in a nice, if you don't have any random error, that is, it will instead shift either up or down. So you will have a y-intercept. I will go into that more when we start analyzing graphs and so on. But this shows systematic error if your line is supposed to be going through the origin, or not. So these are the type of errors. Okay, so the next part that we're going to have a look at is accuracy versus precision. Now, accuracy is simply how close a measurement is to the true value. Like I said before with the example of the value of gravitational field. So if I had we've done experiments and one group got the value to be 9.78 meters per second squared. Another group got 9.18 meters per second squared, and another team, for example, got it to be 10.10 meters per second squared. These are the measurements that we made. So This is what we calculated a G to be in a measurement. However, we know the true value of what has been as accurately as possibly measured is 9.81 meters per second squared. Now that simply means that the most accurate value of all of them is the one that's closest to it, because it's nearest possible one. So like I said, the keywords here to remember is that the true value is the value that has been accurately measured and we definitely know is quite correct. Now, precision doesn't have anything to do with accuracy. In normal everyday life, we do use these two words without realizing that it's incorrectly used. It doesn't matter though, because it's not the same meaning as in physics, but it does really matter in physics, and many people tend to lose their marks in exam questions when they use the words accuracy and precision in the way they shouldn't be. And then we have precision. Now, precision is how closely all the repeated measurements are to each other. So if I measured the length of a spring, again, an unstretched spring, and I kept getting, 5.2 centimeters, 5.3 centimeters, and 5.4 centimeters. These values are quite close to each other. It's basically 5.3 plus or minus 1, which is not a very big difference. So we can say that, oh, my answers were quite precise. However, if, for example, I've done another measurement and I got 6.5 centimeters, now my measurements are getting less precise. So they're getting further from each other. Just going to quickly erase that. The best way of picturing it is by looking at these beautiful diagrams of the bullseye. So if we made repeated measure, if you consider the black dots on the bullseye, these black dots on the bullseye to be the measurements that we make. So imagine taking measurements and your measurements are all over the place, like in the first diagram here. If they're all over the place, that means that there's low precision. So the measurements, all the measurements you made were quite far away from each other. But they're also low accuracy. They have low accuracy because if you notice, they're all spread around the bullseye. Obviously, the bullseye, the center being the actual measurement, the correct measurement, the true value. You do have one value there, but if you consider that everything else spread around it, it's not accurate. Now we go to the second diagram. Remember, this should be your true value. Now, there is no answers within the true value. There is no measurements made, within the true value. Hence, low accuracy. But the measurements are all quite close together. So the repeated measurements are very close to each other, which makes it have high precision. Then we go to this corner at the bottom here. We look at this diagram. A lot of the measurements we made are in the bullseye center, so near the true value, so we have high accuracy, but the measurements themselves are quite spread around, so they have low precision. And then if we look at the last one, this is like the ideal experimental results that you would want to get, but that doesn't always happen, hence why we need to be able to talk about accuracy and precision. All of the measurements are at the bullseye, so very high accuracy, and all of the measurements are very close to each other, so high precision. So please make a note of how important this is in terms of talking about it in physics, especially when it comes to 6-marker questions in exams. These words do pop up in the exams, and you should be answering for the specific word asked. So if they tell you to comment about the accuracy, you have to talk about how close your answers are to the true value. If they ask you to talk about precision, then you need to talk about how to make those measurements get close to each other. So it's very important to differentiate between the one or the other, because you won't be getting the marks in the exams if you talk about accuracy when you're supposed to be talking about precision, or the other way around. And the next part is uncertainties. So when we talk about uncertainties, they always relate to a measurement that we take. So when you use your ruler to measure a specific length, you always have an uncertainty associated with the measurement you take. Meaning, let's say you measure the length of your pencil case, and the length of your pencil case is 15.6 centimeters. Now, obviously, you can't say, oh, no, it's exactly 15.6 centimeters because that's what I saw and that's what I measured. It is actually 15.6 plus or minus 0.1 centimeter. That means that your answer is up or down within 0.1 centimeters. It could have been that it's 15.5, 15.6, or 15.7 centimeters. That's because every single measuring instrument that we use has its own resolution. Resolution is basically the smallest increment measurement, the smallest division on the measuring instrument that you're using. For example, a millimeter ruler, for example, has 0.1 centimeters up or down from the measurement that you take. A thermometer that measures has the smallest division of 1 degree Celsius, it's plus or minus 1 degree Celsius. So if we had a thermometer in the classroom, and the smallest division of the thermometer was 1. So for example, 0, then it has 5 degrees, then 10 degrees Celsius, 15, 20, and so on. Now, if the smallest divisions was 1, 2, 3, 4, 5, and let's say in the room it was about 21 degrees Celsius, so I measured it and I decided it was 21 degrees Celsius, I still can't say in physics when I'm making my measurements, oh, it's definitely 21 degrees Celsius. It is not, because it could be just simply that it is a little bit more into the 21.5 or 22 degrees Celsius, but or up and down from that value. So it's going to be 21 plus or minus 1 degrees Celsius. So, like I said, every measurement has an uncertainty, and it is something that you'll have to get used to throughout the course. You'll learn more and more as we go through it. But the uncertainty is usually related to the resolution, which is the smallest division on a measuring instrument. Like I said, your millimeter ruler has the smallest value that you can read of it is 1 millimeter. You can't read half a millimeter because it's not marked down as half a millimeter. Usually the better the resolution of an instrument, the more precise your values will end up being. However, let's move on from that. Random errors with repeated measurements can be avoided as well by taking the repeated measurements, but I'll go into it a little bit more as we start doing the experiments and analyzing them. So there will be questions asking you to state uncertainties on your own. So for example, for a single reading, so let's say the temperature reading that we were talking here, the absolute uncertainty will be the smallest division on the measuring instrument used, like we showed in this example. But if you make repeated measurements, so let's say I recorded one temperature of hot water, of warm water, and I started recording more measurements of it. So at one point it was 23. So let's forget about this part. 23 degrees Celsius. I'll just redo it. So let's say my first measurement was 21 degrees Celsius. The second one was 23. The third one was 20. And the fourth one was 26. Let's say I got all these measurements. Now these are repeated measurements, which means that I can take the range of the measurements, so from the highest to the lowest. So So it's 26 minus 20. You should have done this in maths before. So you always take the difference from the highest to the lowest measurement that you got, which is 6 degrees. That means, and I divide the value by 2. I also take an average of these values. So the average will be, so I add the mean value, which means I add all 4 together and divide it by 4, which will give me 22.5 degrees Celsius. But my values can't be more precise than what the actual temperature scale can give me. So I have to round up to 23 degrees Celsius. So my answer will be, my mean value is 23 degrees plus or minus the half of the range, which is 3 degrees, plus or minus 3 degrees Celsius. Sorry. And that will be my value with its uncertainty. So this is the value, the measurement, and this is the uncertainty. So this is actually called the absolute uncertainty, which is shows how large the uncertainty actually is and has the same units as the quantity measured. We call it absolute uncertainty because when we take the percentage of it, we call that percentage uncertainty, just to differentiate between the actual value with its unit and the percentage of it. So now if I wanted to find the percentage uncertainty, I'll show you in a second, but it's basically the absolute uncertainty divided by the measured value. This is the measured value, this is the absolute uncertainty, and then you times it by 100 to get the correct percentage. So if that's the absolute uncertainty, then my percentage uncertainty will be 3 divided by 23 times 100. That will give me 13%. That's a very high percentage uncertainty. So obviously you can see from here that the values were far away from each other, so they were quite low precision in these repeated measurements. So this is an equation that you should write down in your notes about how to calculate the percentage uncertainty of any single measurement. So it's going to be the absolute uncertainty divided by the mean value or the actual value, if you only have one single measurement, times that by 100 and you get the uncertainty. Usually always, the lower the percentage uncertainty, the better the value that you have. And we can also discuss later on when we start doing the experiments, how we can make that percentage uncertainty get less and less. But if you're okay with your mathematical skills for now, usually the higher the value you measure, the mean value you measure, and the lower the absolute uncertainty will give you a lower percentage uncertainty in general. So the higher the denominator, the lower the percentage uncertainty you'll end up getting. We will go on now into a quick example about how to deal with some of the uncertainties or how to figure them out if you have certain scenarios. So the first scenario says you took measurements of the diameter of a copper wire and these are your results. So you have 0.53 millimeters, 0.49, 0.52, 0.51 millimeters. Then if you need to find the absolute uncertainty of your measurements, then you get the range. So from the highest, which is this number, to the lowest, you subtract them. The difference between the highest and the lowest is 0.04 millimeters. Then you measure the mean diameter. So you add 4 values and then you divide them. You add the 4 values and then you divide them by 4 since it's 4 measurements. Your mean diameter will be 0.51 millimeters. So your absolute uncertainty should be taken as half of the range of these values. So that will be 0.02 millimeters. And you can write your final answer as 0.51 plus or minus 0.02 millimeters. Just remember that usually is the best way to write and set absolute uncertainties and percentage uncertainties is to one significant figure. You don't need more because usually that goes beyond the point of what an uncertainty is. Now, if all of the measurements you took were all the same, 0.51 millimeters, then your absolute uncertainty should be taken as the resolution of the measuring instrument. In this case, if you could only measure to 0.01 millimeter, then it will be 0.51 plus or minus 0.01 millimeters. And that's because you cannot know possibly what the number there will be if you don't have that part on your actual measuring instrument. That also goes for exam questions. You cannot answer. So you all usually make a calculation and then you all turn to write down, let's say I got an answer of 14.5435678 so on. That's what your calculator will give you. Now you can't really have an answer that's so perfect in terms of numbers that were not existent in the question to begin with, in terms of decimal places or significant figures that were not present in the question. So the best way of answering the questions always is to give your answer to the lowest number of significant figures in the question. We will go through that more as time goes by, but I just wanted to make a quick mention here for that. Now there are, three rules regarding how we deal with uncertainties when we use equations. Now we're going to start with adding or subtracting quantities. So for example, we have an example here, but I'll actually start with what the actual rule is first. When you add or subtract quantities, so if you add length or subtract length, that's what we mean by quantity. Remember, anything can be a quantity that you can measure. So in this case, we're going to be looking at the example of length. So if I add or subtract length, then obviously the new value that I get will also have an uncertainty, just like the measurements are originally made. Now, in order to get the uncertainty of the new value, you have to add the absolute uncertainties for each value. So whether you're adding or subtracting the lengths. So anything you add or subtract in terms of quantities, it could be that you're adding resistance. Then you add the absolute uncertainties of each resistance value that you added. Even if you're subtracting resistance, you do the same thing. You add the absolute uncertainties. I'll write it in a general form. So let's say you have y is equal to a plus b. Then if you want the absolute uncertainty of y, then you have to add the absolute uncertainty of a plus the absolute uncertainty of b. The same thing, if you want to get for y is equal to a minus b, then the absolute uncertainty in y is equal to the absolute uncertainty of a plus the absolute uncertainty of b. Absolute uncertainty, once again, is the actual value with its unit, because things will be different when you multiply and divide. So this is a nice question. It says the original length of a spring is 2.5 plus or minus 0.1 centimeters. Remember, every measurement has its own uncertainty. And the final length is 15.0, meaning after it's been stretched, plus or minus 0.2 centimeters. Calculate the extension. This is a simple question. You should all be able to calculate extensions of springs, because you know if it's extended to that length and you know the original, then what's the extension? And its absolute uncertainty. So I know that the original length is 2.5, the new length is 15. So if I want to get the extension, so it's equal to the final length minus the original length. This expression is similar to this one, well, the same, but with different things. So y is equal to a minus b. If I want to do the calculation quickly, it's 15 minus 2.5 to get the extension, which is 12.5 centimeters. But then it also asks me to calculate the absolute uncertainty of the extension. And since I know that the absolute, if I want to find the absolute uncertainty in the extension, then I need the absolute uncertainty of the final length, which is 0.2 centimeters, plus the absolute uncertainty in B, so the original length. So plus 0.1 centimeters, so that gives me 0.3 centimeters. Hence my answer to this question will be the extension is 12.5 plus or minus 0.3 centimeters. And you can see that they both have up to 1 decimal place, not more, because there's no possible for us to know further significant figures if we can't measure them. So what about if we're multiplying or dividing different quantities, then what will be the uncertainty in the new value that we're trying to calculate? Now if you have, for example, y is equal to a times b, then you need to get the percentage uncertainty of a, and if you want to calculate the percentage uncertainty in y, then you need to find the percentage uncertainty of a and b with that equation I showed you previously. Actually, let me just go back to it quickly. With this equation, if you're not given it directly, then you have to use the absolute uncertainty divided by the value to get the percentage uncertainty, and then use that value in your calculations. So if you want to get the percentage uncertainty in y, then you have to add the percentage uncertainty of a plus the percentage uncertainty of b. The same thing goes when you divide the value. So if you have y is equal to a divided by b, if you want to find the percentage uncertainty in y, then you add the percentage uncertainty of a and the percentage uncertainty of b. So there's an example. The current in a resistor, so this is a current, the symbol for current is I, and the potential difference across the resistor, so voltage, in other words, that you're used to from GCSEs, is, so the symbol is capital V for voltage, for potential difference, is 6.00 plus or minus 0.20 volts. Calculate the resistance and the absolute uncertainty. So it's very key to read clearly what the question's asking. With this format, we will end up with percentage uncertainty, and I'll show you how we're going to solve through that. So if I want to calculate resistance, another equation is R is equal to V over I. So potential difference divided by current. So if I want to find the resistance and the absolute uncertainty in the resistance, I have to follow the rule. Since I'm dividing the two quantities, then I need to add the absolute uncertainties of the two quantities. But I'm given the absolute uncertainties first. I'm not given the percentage uncertainties in these questions, which means I need to calculate the percentage uncertainty first and then add them together. So to do that, I do the absolute uncertainty divided by the value, the measurement, times by 100. Do this for this one as well. So 0.20, which is the absolute uncertainty, divided by the value, times 100. So for this one, we got 1.25% for I. For V, we got 3.33333, but we don't need too many threes, that's enough, percent. And we just add, firstly, if I want to find the percentage uncertainty in R, I need to add the percentage uncertainty of V and I, which is 3.33 plus 1.25, which is 4.58%. Now, if it only asked us to find the percentage uncertainty, I would round this to one significant figure to be 5%. But since it's asking me for the absolute uncertainty, I can keep it to a bit more significant figures so I can get a better absolute uncertainty after. It told me to calculate the resistance too, which is 6 divided by 1.6. This gives you 3.75 ohms. And now we need to calculate, so since we know the actual resistance value, I need to find out, and I know it's percentage uncertainty, so far I know that R is 3.75 ohms plus or minus 5%. Now what's 5% of this value? That's what I'm interested, or I'm going to use actually 4.58% to keep it a bit more precise until the end. Then I'll do my rounding up to 2 decimal places only. So that will be me working out that. So that would be 3.75 times 5%. So that gives you about 0. I've forgotten to put 5%, but let me put 4.58. I just rounded it, so let me just do that again. Okay, so that will be 0.17175. This is too much. I don't need this because I don't actually have a measuring instrument that measures to that depth, to that precision. So what I will end up with is just rounding it up. It will be 3.75 plus or minus 0.17 ohms. That's my resistance with the absolute uncertainty. Now this is the last part, is when we raise a quantity to a power. There's a lot of equations that follow that the power root. So sometimes you'll see power is v squared over r or I squared r. So what we have here is we have a quantity that is raised to a power. So we need to deal with it with this rule of uncertainties. If it has uncertainties in these values, if we need to analyze the uncertainties in the values, depending on what the question will ask you. And also you will need to deal with it in terms of multiplication, which means you have to add them afterwards for r. We'll see more examples in class when we do practice questions. Just be aware that all of these rules can be applied to the same equation depending on what we're doing to each quantity at all times. So let's go with the first one, with what the rule is. When raising a quantity to a power. Now, if we want to get the percentage uncertainty or even absolute uncertainty of the quantity I'm calculating, then I will need the percentage uncertainty and I need to multiply it by the power that it is raised at. I'm just going to do an example because I do believe that examples actually provide more vision into what you actually need to be doing. So tells me that the diameter of a wire is recorded to be this much. Calculate the cross-sectional area of a wire. Now remember, wires are like small cylinders, yeah, extremely small cylinders, and the absolute uncertainty. So the cross-sectional area is a circle, quite obvious. So that means I need to calculate the area of a circle, in other words. of the wire using the diameter. You know that to get the area of a circle is pi r squared. We know that diameter is the whole length. So if this is the circle, this is the diameter, and this is the radius, half of it. So in other words, radius is diameter divided by 2. So I'm just simply going to use that, pi d over 2 squared. So it's pi d squared over 4. Very important thing here is that when we have constants or numbers, they don't carry an uncertainty themselves because they're fixed numbers. So pi then doesn't have its own uncertainty. 4 does not have its own uncertainty. But d does have, the diameter does have its own uncertainty. So based solely on diameter, the area will also carry an uncertainty. And that's the uncertainty that I need to be able to calculate, the absolute one that the question's asking me. But first I have to deal with the percentage uncertainty, because if I raise a power, a measurement, when a measurement is raised to a power n, your percentage uncertainty is multiplied n times. So once again, we deal with percentage uncertainty. So I need to find the percentage uncertainty of this value of the diameter. And to do that, I do 0.02. So the absolute uncertainty divided by the value times that by 100. That gives 3.92%. And my power in this case is 2, because it's d squared, so 2. So I have to do 2 times 3.92, which gives me 7.84%. Obviously, like I said before, we need the absolute uncertainty, so I'll do my rounding up at the end when I'm finished. If it was asking me for the percentage uncertainty, I will leave this value, I will round this value to 8%. Because one significant figure for percentage uncertainty especially is enough. But for now, it's not asking us for that, so I'm not doing the rounding up yet. And obviously I need to calculate the cross-sectional area, so I just make sure that you convert your units, very, very important. Millimeters is that. So area is pi times 0.51 times 10 to the minus 3. We always need to be using meters, so we convert all the time. Divide that by 4, squared, divide that by 4. So I get this answer. However, the measurements I've been given are given to 2 decimal places, so I can't leave this number so long because it's not accurate. This is not precise or accurate. I need to get rid of this 2 and leave it to 2 decimal places, or to 2 significant figures to be more accurate. But in this case, let's just leave it to 2 decimal places because that will be better for our answer. So that will be 2.04 times 10 to the minus 7 meters squared, plus or minus 7.84%, meaning the answer is up or down nearly 8% of that. So to find the absolute uncertainty, I just simply need to multiply this number by 7.84 divided by 100. So that would be 2.04 times 10 to the minus 7 times 7.84 divided by 100. That gives me 1.6 times 10 to the minus 8. This is the answer that I get, but I want it to be to the same order of magnitude, so my answer looks better when I write it down. So I can change it. Remember, if you times it by 10, then you can put the dot on this side, and then you get a lower power on this side. So that will be my complete answer. The area is 2.04 plus or minus 0.16 times 10 to the minus 7. But, like I said before, my answer is only to 2 significant figures. So I'll just simply change my answer to two significant figures, which leaves me to 2.0 plus or minus 0.2 times 10 to the minus 7 meters squared. For the last point in the learning outcomes, this will be covered in class, as we need graph paper and questions near the time where we start doing more questions regarding actual experimental work for it to make a bit more sense. It will make much more sense. You'll be given information for this. If you have any questions, please also note them down at the end of your homework, and we'll go through them in class.